Hey there. So I got your messages with these videos or with the pictures, and here's a video with some explanations. Hopefully this will make sense. Send me some questions if you have any, and we will talk about it. So the first thing on there was about energy diagrams. And when we are talking about reactions, what makes them happen is typically putting energy into this reaction to kick it off. Or sometimes things happen spontaneously, meaning they already have enough uh, energy in it to cause a reaction to happen. And we can plot those energy changes and specific important points in a reaction using a graph. So an energy diagram looks something like this. And this is reaction progress. So as the reaction goes, this is how it is changing. Over here, we have potential energy because reactions happen because of energy changes. So we start with our reactants over here, and then it'll make a curve, and then it will either level off up here or down here. So these are our reactants. These are our end products. This is our transition state. It is the amount of energy that has to go into this reaction to even make the reaction take place. So once we hit that threshold, put in enough energy, then we start forming our products. Now, when we're talking about energy going in, it's often described as delta H, which is enthalpy. We can think about enthalpy as the amount of heat either going into or coming out of a reaction. When something is exothermic, meaning that energy is leaving that system, then our enthalpy will be a negative. Think of it like energy going out of. If it's endothermic, then energy is going into the system and del H is positive. So let's think about this looking at a graph. We start with our reactants. We put energy in, energy in, energy in. We hit that transition state. The reaction proceeds and takes place. So then we start forming products. And now our energy is higher than it was when we started, right? There are sections of every reaction that are endothermic, right? Energy going in to make it happen. And then there are parts that are exothermic. And you can figure out is the overall reaction endothermic or exothermic based on which parts of these is bigger, or do we have more energy than when we started? So in this case, we do have more energy than we started. So this would be endothermic. As opposed to this, we still have our reactants, we still have our products forming, we still have our transition state, the amount of energy that we had to reach for the reaction to even take place. The reaction takes place, we release energy, release energy, release energy, and we have our products. So this one would be exotherm. We can also calculate things from these graphs. So there is our activation energy, often written as E sub A. And that is the amount of energy to get to the transition state. So it is from our reactants here, our starting energy, up to our transition state. That is our EA. Excuse me. And it's just defined by the amount of energy that it's going to take us to go from our reactants to make the reaction even happen. You can do that by adding heat, putting it on a Bunsen burner. You can do that by using certain types of light. certain energy waves will impart that energy into a reaction and make it go. So this is the amount that you have to put in to even make it happen. The overall energy of the reaction is going to be our difference between our reactants and our products, or our products and our reactants. So from here to here, right? I don't know if you can see that. Let me put that over here. Yeah, it's a little bit back. Okay, so difference between here and here. And that is the energy of our reaction, or the overall enthalpy of the reaction. So it's products, energy, minus our reactants. Okay. So they may give you a reaction, say this is exothermic, draw the energy diagram. So depending on whether or not it's exothermic, you would start with high energy, hit your transition state where it levels off, and then end up with less energy. So that's exotherm, endotherm. Start with your reactants, put energy in, hit your transition state, and you end up having to put more energy into that reaction than you get from your products. I hope that makes sense. Your second slide um, is discussing rates of reaction. So when we are plotting these things, typically, they're you do it over time. The rate of a reaction is how much the concentration changes over time. So if we were writing that, we would say rate equals change in, I like the little brackets. You can also do change in C over change in time, right? This delta means change. So in the slide that you had sent, this was CH4 plus 2O2 goes to make CO2 plus 2H2O. I believe this is balanced. We know this is a combustion reaction because we are adding O2 into this and we are getting CO2 and H2O back. All three of those things tells us this is combustion. We are heating it up. We are getting water and CO2 in return. And they give us a little more information. They say, calculate the average rate of the reaction if the reaction begins with no carbon dioxide, but after 1.2 hours, there exists 1.2 molar concentration of CO2. Okay, so we said that after 1.5 hours, so that's our change in time, right? We're going from 0 hours to 1.2 hours. And our change in concentration, we're going from 0 concentration to 1.2 molars. So that's our change in C. So we can write this rate equation as rate equals change in concentration, so 1.2 molar over 1.2 hours. So we are changing at a rate, at a rate of what? 1 to 1? 1 molar per 1 hour. So this is how we would think about these graphs, right? How much is this concentration changing over time? The next slide that you had sent was, it showed a clock and, showing a time. And then there are pictures with different molecules in them, right? And as it progresses, you get more of these boxes with increasing numbers of red in there over the black as time changes. So this is just kind of showing you visually how a reaction would take place. We're forming more and more and more products. The concentration is getting higher and higher as time is changing. So it's just another visual representation of this. The next slide was on the Haber process. It was N2 plus 3H2 goes to make 2 ammonium molecules. And this is just, I think, how they were describing reactions take place. This would be, ooh, give me one sec. I need to see if they go into talking about types of reactions in this chapter, because if not, this is going to be a whole thing. Okay, we'll swing back around. I'll make a different video about this one because I don't want to have to edit this one too much. So let's see. We talked about writing the rates of the reaction. We talked about our energy diagrams. We talk about what all of these things mean, right? As the reaction progresses, this is how it changes. We can plot concentration over time, and I believe you do that in a lab. The other thing that you had sent was on equilibrium. So that's going to be a whole separate video because equilibrium is a very big topic, and I don't want to miss anything. I don't want to rush through it. So practice what you have about these ones. I believe that there's some Alex in there. And then I will make you another video on equilibrium um, to give you kind of a preface on the ideas of equilibrium. We know that a reaction goes back and forth by seeing these arrows, right? When we see a reaction written, typically, well, so far you've only seen this one arrow. That implies that, okay, these are reactants and these are the products that are forming. That's it. But not all reactions work that way. A lot of reactions happen, they go back and forth, especially in the case of chemical engineers. They design chemical reactors and they need equilibrium to be reached. We can affect this equilibrium and what that, hold on, let's talk about this first. What equilibrium actually is not saying that we have the same number of or the same amount of reactants as products. What it is saying is that we are forming products at the same rate as we are forming reactants. Equilibrium is about rate, which is how it ties into all of this, right? So it is the rate that uh, forming products and reactants is the same. And we can affect where this equilibrium point is a few ways. One is by changing our concentration. So changing concentration, right? Um, when we add reactant in here, then think about this kind of like a seesaw, right? Right now, we are at equilibrium. We have the same thing going on over here as we do over here. But when we add a little bit more to one side, what's going to happen to the other? Well, this comes down, this goes up, and we will need to add more over here to reach that equilibrium again. So we would say that when we add reactant into this equation, equilibrium favors the products. And conversely, if we remove reactant from this equation, this side becomes lighter, and we would have to add more into the reactants to rebalance that out. So we would say equilibrium favors the reactants. And think about it in the reverse. If we add product, this side becomes heavier. We need to add more of the reactant, so we would say it's reactant favored. So changing concentration is one of the things that we can do to affect equilibrium. The second thing is temperature. So changing T. And when we increase temperature in equilibrium, what we're really doing is speeding up those molecules, right? And when we speed up the molecules, there's a higher chance that they are going to run into other molecules, causing the reaction to happen. So higher concentration typically results in faster reactions. You would see that in comparison on one of these graphs by having a shorter amount of time to reach that transition state, right? That's how you would tell what is a faster or shorter reaction. If it doesn't take as much time to get up here, it's going to be a shorter reaction. It's going to go very, very quickly. Much like when we think about a roller coaster, right? You're up here, it is taking a while, taking a while, taking a while, taking a while, and then the reaction goes. So if we are on a very small roller coaster, it doesn't take a whole lot of time to get up here, and then the reaction goes. So increasing the temperature, if it is an endothermic reaction and we increase the temperature, equilibrium is going to go towards the products. So we are speeding up all of these molecules to get it to that transition state, and then it forms the products, right? So in exothermic, it's backwards. We increase the temperature, and equilibrium will favor the reactants because we have this energy output over here, right? With exothermic, it means more energy is leaving the system. So if we are increasing the temperature, more products are being formed. So we would need to up the reactants, right? To re-level this, thinking about that seesaw analogy again. So if we decrease the temperature in an endothermic reaction, then equilibrium is going to favor the reactants. We're going to slow down those molecules. They're not going to be forming products running into each other as quickly. So we would need to increase those reactants again when we are decreasing the temperature in an endothermic. In exothermic, when we're decreasing the temperature, right? So exo, we're putting out more energy than we are putting in, and we are slowing the molecules by decreasing the temperature. Then equilibrium will favor the products. Pressure is the third thing. So changing in pressure. Pressure is often given in ATM. You might also see it as mmHg, that's millimeters of mercury. And when we are increasing temperature, let's think about this is a closed system with pressure in it, right? And we have a plunger. And we have these gas molecules. If we are pushing down, right, and increasing this pressure, uh, pushing down, increasing pressure. Sorry, I wrote this really confusing. This means that we are increasing our pressure by pushing this down. Very confusing. Then we are lessening the volume that is in here, and the gas or whatever it is in there will have less room to move around. So they're going to be running into each other more frequently than they would with more room, right? Spread out. So when we increase the pressure, equilibrium is going to favor the side of the equation that has fewer moles of gas. So if we are looking back, this is the Haber process, right? These are gas. I should have written these in here earlier. And we said that we are increasing the pressure. We are pushing this plunger down, making it so these molecules are running into each other at a faster rate. Then equilibrium is going to favor the side with fewer moles because there is less chance of those molecules hitting each other, right? So here we have 1 mole of N2, 3 moles of H2, making 4 moles of gas over here versus our 2 moles of gas over here. So we said increase the pressure, right? Making those molecules bump into each other more frequently. And then equilibrium will favor the side with fewer moles. So this would be product favored. We are increasing the pressure. If we are decreasing the pressure, then equilibrium will favor the side that has more moles of gas. So this side, if we are decreasing the pressure, we are lessening that volume, or we are giving it more volume, right? Giving those molecules more space to move around. So equilibrium would favor the side that has more moles when we are decreasing pressure. There's just kind of a preview on equilibrium. If I were you, I would absolutely go through and do all of the extra material for this chapter. It will absolutely help you. Do not look at the answers until after you try the problems. I believe it's Le Chatelier. That is the concept of equilibriums, Le Chatelier's principle. That's what all of this is, primarily focusing on changes in concentration, changes in temperature, and changes in pressure, and how that will affect, is this reactant or is this product favored? Think about it, like this? What is going to happen when we increase this or decrease this? Also, I would do the um, reaction rates activity. And sorry, I'm clicking through this right now, so I want to look at what I'm telling you to do. And I believe there is one more. Go through and look at those. If you run into any issues, circle it, send me a picture. We can talk about it. Um, it's mostly, it looks like it's asking a lot of the same questions that we just talked about. How is changing this one variable going to affect our equilibrium point, where that rate of reactants forming is equal to the rate that we are forming products? And then I think there is one more activity in there that I would recommend doing. Yeah, writing equilibrium expressions. So when we are writing an equilibrium reaction, right, we said that this was about the rate that we're forming products and reactants. So if we were writing that, we would write it as K. A lot of things in chemistry are written as K. So you might also see it as KEQ, right, equilibrium. And we would write our change our in concentration of products over concentration of reactants.